Here you can see our absorption column. The absorption column consists of many different dials, many different valves, and controls in order to adjust the flow rates of the air, the carbon dioxide, and the water in your system. The water tank is located here, and it is filled using this water connection on the wall. You turn that on and you can fill up the tank, and you want to ensure that the water level remains between the upper and lower pink pieces of tape, ideally around the green tape, to avoid having too little water or overflowing that tank during the experiment. This white machine here is our air blower. So this air blower can be turned on and off and will allow air to be pushed through your system. On the main control here, you can see a pump switch. So by turning this on and off, you can control the water pump in your system and whether or not that is functioning. Here is a blower switch, so you need to turn on and off that switch to control your air blower. And then here is a rocker switch for CO2. So this you will flip up or down depending on if you want your inlet or outlet CO2 to be read by the software. Here you can see two knobs labeled V2 and V10. V2, if we trace the tubing, we see is attached to our air blower. Therefore, by adjusting V2, we can adjust the air flow rate through our absorption column. And the value of what is being pushed through the column will be read out both on the screen of our absorption column and in the software on our computer. Here is knob V10, and knob V10, if you trace that tubing, is connected to our water tank. So that knob is used to control the water flow through our absorption column, which again, the value is read out on our screen and in our software. From the top to the bottom of our column, we have three valves labeled V11, V3, and V4. These valves are used for reading the differential pressure along our column. V3 is kept closed, as you can see, but if this is open to the atmosphere, we read our pressure differently. But we want to keep that closed so that we can read gauge pressure through our software in order to use those values properly rather than having to account for atmospheric pressure. In order to control the flow of carbon dioxide through our system, we first need to turn on our carbon dioxide. The carbon dioxide tanks are located all the way across the lab in this back corner, and those are attached to a pressure regulator. Generally, these tanks are turned on and you don't need to worry about opening or closing any of the connections, but if necessary, instructions for that are in the manual. And on the ceiling here is a small valve which is labeled CO2. So you need to get a ladder, which is right here, in order to open that valve to the system, and then you can control the flow of the CO2 using this knob here. When samples must be taken at various time points through the experiment, we use this valve here, which is labeled V5. We lift this lever and turn it forward in order to allow water to drip out of this valve into our collection vessel. Samples which are collected from the absorption column must be titrated using this setup in order to determine how much CO2 is present. You will have prepared a sodium hydroxide solution prior to the experiment, which will be filled into the burette. Before you do this, make sure that this valve, the stopcock, is closed so that your solution doesn't immediately drip out. And you want to record the initial value of the NaOH solution in that burette prior to your titration. Then you will allow the solution to drip into your stirring flask containing the collected solution, which also contains an indicator which will allow your solution to turn pink when the appropriate amount of NaOH has been added to your solution to neutralize the CO2 contribution. These titration experiments are run side by side by two students and must be run very quickly after the samples are taken. This is because since we are trying to measure how much CO2 is absorbed in the water, and CO2 is a volatile gas, if we leave that sample sitting for too long, the CO2 can bubble out and we will not get an accurate measurement for how much CO2 was actually absorbed within the column. Under normal operation, the absorption column should look something like this, where there is fluid running along the packing material, but the entire column is not filled with water. Of the experiment which you will run is to observe flooding in the column. This occurs when you see something like this, where the water is accumulating on top of the packing material and is not simply coating the outside of the material anymore, but actually accumulating within the column. You can also see some siphoning down here when flooding is occurring, and this is not proper operation for the column and occurs when your water and or airflow rates are too high, either individually or in relation to